Okay, so welcome to our last video for this unit where we put everything together and relate equilibrium with thermodynamics with electrochemistry. Now the equation to relate these, so we're going to be relating, so whenever we're talking about thermodynamics, we're talking about delta G, and for electrochemistry, we're going to talk about cell potential. The free energy change of the reaction is negative N times Faraday's constant times the cell cell voltage that you would calculate. N, keep in mind, in this case is going to be the number of electrons from the balanced half reactions once you actually equalize the number of electrons. Right, so go through the step and then right before you combine them, so after you've gotten the same amount of electrons in each half reaction, that's what your N value is going to be. F is still the Faraday constant from our electrolysis math. And the other thing to keep in mind is that Gibbs free energy for all of these problems has to be in joules, right? Especially once we start using ideal gas constant, you need to have joules for this instead of kilojoules, right? So that is the equation to relate thermo to electro. So what this basically means is that anything that produces a positive cell voltage is spontaneous by definition. Now for equilibrium constants and delta G, the equation is that the delta G standard of reaction is negative RT ln of K. Keep in mind again, this R is energy R because delta G is measured in joules. Right, so any reaction which is product favored will be spontaneous by nature. Now I'm going to show you an equation. You are probably not going to have to use this on the AP exam, but it's nice to show you guys anyway. And this is what to do if you are not at standard conditions. Right, so delta G of a reaction not at 298 Kelvin. All you do is you take your standard delta G and you add RT ln of Q. So you go through, you calculate the value of Q and plug it into the regular delta G value that way. So if I were to, for example, give you a reaction and say, at 304 Kelvin, these are the concentrations, you would take Q at that temperature and just plug it in and add it to the delta G that you would get from doing your delta H minus T delta S. And then our last one is going to be electro in equilibrium. So this is cell potential and equilibrium constants. So the standard cell potential, again, at 298 Kelvin, RT over NF, ln of K. So again, R is still going to be energy R. N is still the same number of electrons from the balanced and equalized half reaction. F is still the Faraday constant. Right, and then you take the natural log of K. So anything that is product favored or anything with K less or K greater than 1 will have a positive voltage. Now the extension to this, and this equation kind of looks familiar if you talk about Gibbs free energy, this is what's called the Nernst equation. And this is how to find the cell potential of any cell not at standard conditions. So if we change temperature or if we change concentrations, right? Because again, standard conditions are considered 298 Kelvin, 1 molar solutions. If we change from that 1 molar, we can calculate the difference here. If you want to look up a very interesting application of the Nernst equation, look up something called a concentration cell. Right? Basically what happens is that if you take two half cells that have the same exact substances in them, so like for example, copper nitrate in each half cell with copper electrodes, as long as the concentrations are different in each half cell, it will actually produce a very, very, very small voltage. I've seen places on the AP exam where the Nernst equation could be useful. It is not required. Again, any question that you can solve using the Nernst equation can also be solved by comparing Q and K. If you want to use it, go ahead and use it, and they will not take off points if you use it correctly. If you don't want to use it, there are always going to be alternatives for you. Right, so that is relating equilibrium, thermodynamics, and electrochemistry in one nice, neat little package.